Hello everybody, today we will be talking about related rates in calculus, and so this is the first time that we're going to be seeing some sort of modeling problem for calculus, so then that way you can kind of look at it as an application then. So here is an example of a related rates problem, and so let's go ahead and decipher this and figure out how to attack it or create some sort of strategy then. Okay, so here's the setup. We have a ladder that is leaning against the wall, a vertical wall. If the bottom of the ladder is sliding away from the wall at a rate of 1 feet per second, I want to know how fast is the top of the ladder sliding down when the ladder is 6 feet away from the wall. So here is a generic situation or generic picture of the situation that we actually have. And as time progresses, what's going to happen is that for this triangle, according to this problem anyways, is going to be more slanted in a sense that the height of the ladder is still going to be the same, which is 10, or the length of the ladder is still going to be 10. X, on the other hand, is going to get bigger and bigger, and Y is going to get smaller and smaller. Now, that's over time as to what's going to happen. So you can kind of see in motion as to what's going to happen. And hence, that's why some people would say that this is kind of like a calculus in motion type of problem. Well, anyhow, going back to what we were saying or what's given, let's go ahead and write them down so we can set up the variables. First, we are told that the bottom of the ladder is sliding away from the wall at a rate of 1 feet per second. So since the denominator, since the variable in the bottom is represented as x, then that means that dx dt, the rate at which x is changing, is supposed to be then equal to 1. And the unit for it is supposed to be feet per second. So that's one of the known then in this case. What I would like to solve for is how fast is the top of the ladder sliding down when the ladder is 6 feet away from the wall. So in the same manner, then that means I'm trying to solve for dy dt. So that's going to be my question mark. And most likely the unit there is going to be in terms of feet per second as well. So, we'll keep that in mind. And the last information is that when the ladder is 6 feet away from the wall. So that means when x is equal to 6. So right there, those are my given. And there's an illustration on the left-hand side. Let's now come up with an equation so we can solve for all of this. All right, so first, the first thing I notice here after we set up everything is that we have a triangle always. So the first thing that comes to mind is, okay, well, why not set up the Pythagorean theorem, because that will relate the two variables. So then that means that we have first x squared plus y squared is equal to 10 squared. And I'm not going to write a variable for the length of the ladder because it's always going to be 10. So we always want to keep that fixed. Remember, in math, you want to minimize the number of variables that you're actually using. All right. So according to the given, I think I can actually solve for y because if you notice, x is equal to 6. So why don't we go ahead and do that first? So 6 squared plus y squared is equal to 10 squared. So y squared is equal to 10 squared minus 6 squared. And just to show a little bit of tricky math right here, the right-hand side, we have a difference of square. So that's going to be 10 minus 6 multiplied by 10 plus 6. So that is now going to give us something nice. Y squared is equal to 4 multiplied by 16. So if I try to take the square root of both sides, we get y is equal to 2 times 4, which means that the height is going to be equal to 8 at that instantaneous moment. So I'm going to go ahead and keep that on the side when height is equal to 8 feet per 8 feet, and then when x, the length is supposed to be equal to 6 feet. All right, now that that's out of the way, we want to start implementing the dx dt and also dy dt. So what that means is we need to take the derivative of the function that's given in order to introduce the derivative. So I'm going to go ahead and take my equation right here and take the derivative of both time with respect to time. So that is to say, I want to take the derivative with respect to time of what I have. X squared plus y squared, right, d dt, is equal to the derivative with respect to time of 10 squared. And that way, we can now go ahead and introduce dx dt and dy dt. Well, some people ask, okay, well, why am I not taking the derivative with respect to x or with respect to y? Well, the reason is we don't need those. We need it with respect to time. Okay, and what that means also is we now need to use implicit differentiation to solve for this. All right, so let's go and see how that works out. First part, if I take the derivative of x squared, the derivative normally would be 2x And then, because it's with respect to time, then implicit differentiation says that multiply by dx dt, and that's how we're going to introduce it. Plus y squared, if I take the derivative normally, it'll be 2y. And then, because of with respect to time again, then that means by kind of like chain rule, that's where dy dt is going to be introduced. Then we have the derivative of 10 squared, and the derivative of a constant, well, then is equal to 0. Okay. Now, had we have taken x is equal to 6 or x or y is equal to 8 and plugged it in at the very beginning before we take the derivative, like say over here, let's go ahead and plug in x is equal to 6 because it was given to us. 6 squared plus y squared is equal to 10 squared. And if I take the derivative of that, we're going to get 2y dy dt is equal to 0. And unfortunately, that does not work, or that doesn't make sense in this problem, because that is assuming that x is always going to be equal to 6, and that's not true. X is a variable that is changing. It's getting bigger or smaller depending on what the time is. So we need to keep it as a variable, so then that way we can take the derivative then as a result. So in short, we don't plug in any of these numbers that we solve for until very end. Now, let's go ahead and do the plug-in then. Here we have 2, which is going to be just 2. X is going to be 6, and I'm actually going to go ahead and write in the units, and we don't actually have to do that, but I want to show that it actually works out nicely if we do. So multiply that by dx dt, and then plus 2y multiplied by, y we actually solved for also, so we're going to go ahead and replace that as well. Y is equal to 8, so that's going to be 8 feet right here. And then dx dt, we also know that is supposed to be 1 feet per second. So let me go back over here and make that substitution as well. And let me make this a little bit bigger just so that we can have a little bit more space too. So 2 multiplied by 6 feet. And then dx dt, that is supposed to be 1 feet per second. Okay. And then multiply by over here, dy dt, which is what we're trying to solve for. We don't know what that is, so we're just going to go ahead and leave that alone. All that is equal to 0. Note, we want to get dy dt all by itself, so let's go ahead and start isolating some terms. The front part over here, that is going to say 12, and it looks like square feet per second, which doesn't really make too much sense. Then over here, we have 16, and that's in terms of feet. And then we also multiply that dy dt. Focus, I want to solve for dy dt, so let's go ahead and move the 12 over to the right-hand side. So now we have 16 feet multiplied by dy dt is equal to negative 12 and then square feet per second. And if we now divide by 16, then we have dy dt. So dy dt is equal to negative 12 over 16, and that's feet squared per second divided by feet. And if you clean that up, that is the same thing as saying negative 3/4, and that's going to be feet per second. So that right there is going to be our answer. And it's just as we said earlier, since we're solving for dy dt, that's the rate at which the height is actually going to be decreasing, and it is negative because it's going downward. In addition, like we said, it's also going to be feet per second because dx dt is in terms of feet per second. When you do this last step right here, do you have to write out the units? The answer is no. I just wanted to do it one time to show you that, yeah, everything actually comes out to be legit in the very end, and you're not just solving for some random number then, okay? So let's go ahead and talk about tactics. Let's talk about, like, how to actually attack these type of problems. Step 1, I always try to take everything that's given to me and write it all out numerically. So meaning, what are my variables? At an instantaneous time, what are my rates, like x, what is my dx dt, what is my y, what is my dy dt, and so forth. We write down everything that's given. Step 2, afterwards, we're going to find the equations that will relate the variables. There might be more than one, so that's why I say equations possibly in this case. We're fortunate to only be able to run into one. Now, next one, after we find the equations, then we're going to go ahead and solve for all the numerical values that we could have solved for in the other missing variables. So this is the case where we were given x, if you remember, and we solved for y on the side at that instantaneous time, because sometimes we might need that value. Next, the step would then be to take the derivative of the equation in part 2 where you related to two variables. And then after you take the derivative, the last step is to plug in all the numerical values that you were given from part 1 and also the ones you solved for in part 3. Okay, so those are always going to be my every single step, and it always works like 100% of the time. All right, so let's go ahead and look at another problem. So we're going to go ahead and use that strategy once again so we can hopefully solve for this. Okay, what we have here is water is leaving a conical reservoir at a rate of 50 cubic meters per minute. So that means that the water is being drained, probably from the bottom. So you can kind of maybe draw something that is like dripping out or something like that. Okay, the reservoir has a base radius of 45 meters. So you can see at the very top is going to be 45. And remember, this is a conical reservoir, so that means it's a cone. So that's why the radius is at the very top. And the height is supposed to be at 6 meters. So what is happening is that you have some water that's inside the tank, and let's go ahead and make it green so that it's like Kool-Aid or whatever, right? So here is the water at a certain height and a certain surface. So that right there is going to drain into the bottom. So then as a result, a little bit later on, you're going to have less water. So it's going to be a little bit lower. And then over time, it's going to be fewer and fewer and fewer and fewer and fewer and so forth until eventually the tank is going to be empty. Okay, so that's the calculus in motion part. Now let's go ahead and set up everything that we do know. So then that way we can figure out what is it that we're trying to solve for. In this problem, it says, how fast is the water level falling when the water is supposed to be 5 meters deep? So at an instantaneous time, we know what the height is, which is supposed to be 5. Okay, starting from the very top, here's what I noticed then. The rate of the reservoir, the rate at which the water is leaving the reservoir is supposed to be 50 cubic meters per minute. So that right there is telling me the following. dV dt, right, V for volume, the rate at which the volume is changing, is supposed to be equal to negative 50 cubic meters per minute. So that's the first information. Now, the next part is that we have a height of 6 at the very top and a radius of 45 meters at the very top. But at an instantaneous moment, it's going to be something else. So we have to watch out for this. So here's what I'm going to do. In our picture, you'll notice that I drew kind of like a small little situation where at a certain instantaneous situation. What I'm going to do is I'm going to go ahead and call that at that instantaneous time, we have a certain radius, which we'll call R. And then we'll have a certain instantaneous height, which we'll go ahead and call H, right? And R and H is going to change according to what we were saying, because again, remember, the water is leaking out from the bottom. So R is getting smaller just as H is getting smaller. Those values, those variables are related to each other, believe it or not, according to that 45 and the 6. So we're going to have to find out that relationship. Nonetheless, let's go ahead and finish up what else is given. How fast is the height of the water changing when the water is supposed to be 5 meters deep? So that means, according to this problem or the setup, I want to know what is dH dt, right? Because height is my variable h, so that's why I want to solve for dH dt. That's what we're looking for. When the water is supposed to be 5 meters deep, so that means when h is equal to 5. So all of this is happening at an instantaneous moment, and that's what we have to work with. All right, so now that we have all of that, let's go ahead and see if we can relate some of these variables together. So number 1, like we said, we wrote everything down. Perfect. So that's part 1 right there. Number 2, we said to come up with some equations to relate all the variables. I have, in terms of variables, the volume. I have also, in terms of variables, the height and also the radius. Okay. So what I'm seeing is the following. I am seeing that the volume, the height, and the radius, well, how about the volume of a cone then? So my equation for that is volume is equal to 1/3 pi r squared h. Okay, so that's going back to geometry, where you're looking at the volume of a conical section, right? So it's supposed to be a cylindrical cone, 1/3 of its volume. So that's where I came up with that then. Okay. All right, so that is my equation for all those three variables. Now, are there other equations? The answer is yes, because again, if you look at my picture, if you take it and break it into two dimension, you'll notice that what I can do is relate R and H together. So here at an instantaneous moment, right, at the very top is still 45, and the height is still equal to 6. But now, when we look at an instantaneous moment over here and over here, here's R and here's H then, okay? According to proportionality, then we can say the following. 45 over 6 is equal to R over H, okay? So that is my proportionality. All I've done was just use what we learned back in geometry to apply to what we have right here, okay? Now, let's go ahead and see what we can do with everything that we came up with. Supposedly at this point, we have all the equations that we need, and we would like to take the derivative of our equation. So then that way we can start introducing all of these derivatives. Well, which equation am I going to take the derivative of? Well, that's probably this big guy over here, the volume equation. Now, let's think ahead a little bit. If I'm taking the derivative right now with respect to time, d dt to both sides, here's what I'm going to get. I'm going to get dv dt. Great, I need that because I have dv dt to plug in. On the right-hand side, it's going to be pretty nasty, but we're going to take the product rule, and we're going to end up with dr dt and also dh dt. Well, that right there is kind of problematic because, look, we don't actually have dr dt, and we don't want dr dt, okay? We don't want to solve for extra stuff that we don't actually need. So the question is, well, how do we deal with this r squared if we don't want it? Well, that's where that second equation comes in, because look, if we can make a substitution to get rid of r, then my volume is strictly in terms of h, and that's nice because then we only have dh dt to worry about. So let's go ahead and make that substitution. According to this, let's see, we're going to go ahead and cross multiply to get the following. 45 multiplied by h is equal to 6r. We divide both sides by 3, so we get 2 over here. Divide by 3, so that's 15 over here. So it looks like r is going to be equal to 15 over 2h, okay? And that right there is going to be my substitution into this equation before I actually take the derivative. Again, I'm doing all of this because I don't want to deal with dr dt when we take the derivative. There's nowhere in the given that we have dr dt, so we want to try to avoid it if possible. Okay, so now let's go ahead and make a substitution. So v is equal to pi over 3, right? We still haven't taken the derivative yet. R gets replaced by that, so that's 15 over 2 h quantity squared multiplied by h. So clean up the math a little bit. So I see 225 pi divided by 3 times 4, so that is equal to, well, just 3 times 4. And then we have h cubed. Cleaning that up a little bit more, can we do that? We kind of don't, well, I guess, no, we can just go ahead and live with that, okay? So there it is. That's going to be my v equation. So now let's go ahead and take the derivative with respect to time. So d dt both sides. So on the left, we have dv dt, right? The derivative of v with respect to time. And on the right-hand side, let's see, that is going to be 225 pi over 3 times 4. The 3 goes down because of the power rule, times h squared because, well, power rule, and then multiply by dh dt because of implicit differentiation. So now we can see the 3 goes away, which is nice. And if you look at now what we can plug in the dv dt, so that's equal to negative 50 over here. And then we also have the rest of this stuff, so that's 225 pi divided by 4. H, that's equal to 5, so we can go ahead and plug that in too. So we're going to get 5 squared and then dh dt. So we're almost done right here. Again, notice that this time I did not write the units because that's going to be kind of like messy, get in the way. So we're going to go ahead and take care of that a little bit later. Okay. So nonetheless, let's move everything over to the left-hand side. That's not dh dt. So dh dt is equal to, so 50 stays over there. We multiply by 4 to both sides, and then we divide by 225 to the bottom. We divide by pi to the bottom, and then we have 25 on the bottom too. So let's see, what does that equal to? That's just a big mess right here. So 50 and 25, they go into each other 2 times. So it looks like in the very end, you're going to get -8 on the top and 225 pi on the bottom. And that's going to be my dh dt. And if you're wondering what's the unit for that, well, there's a quick way to figure that out. Look at the unit from the very beginning, right? Notice that it's in cubic meters per minute. So that is the volume, which is 3 dimension. If you're trying to solve for dh dt, which is 1 dimension, then the unit for that would then be equal to meters per minute then. Okay, so that right there would then be your answer. All right, so that's the first part. And finally, now let's go ahead and deal with the second part over here. How fast is the radius of the water surface changing? So this time in part B, I want to solve for dr dt then. I want to know what dr dt is at that same instantaneous moment. So note how r now is going to be available, and now we're going to have to kind of play around with it. Well, if we want to solve for dr dt, one might think, okay, we can go ahead and take everything and plug it back in and do exactly the same thing as what we did in part A. Basically, replace h in terms of r and then solve for dv dt, solve for dr dt, and plug everything in. But you know what? That's way too much work. We have everything we need right above it right here. Look, 15 over 2h is equal to r. If I take the derivative of that equation with respect to time, we're going to be done. There's no point of reinventing the wheel. So if we take the derivative, here's what we get. 15 over 2 multiplied by dh dt, okay, is equal to dr dt because we're taking the equation, the derivative with respect to time. Now dh dt, hey, we got it. We have that answer right there to the left of us, right? Because we already solved for it in part A. So finally, we just go ahead and plug that in, and then we're done. So 15 over 2 multiplied by dh dt, which is -8 divided by 225 pi, right? And then that's going to be equal to dr dt. So let's see, 225 and 15, they go each other 15 times. So our final answer for the bottom part is going to be -8 over 30 pi, and that also is in terms of meters per minute because that is the radius. So that is going to be our rate at which the radius is going to be decreasing then. All right, so definitely a lot of work. Thank you so much for watching, and I will go ahead and see you guys next time. Okay, take care.